We're about halfway through our two-dimensional forces unit, so it's time to talk about circular motion. So, let's start with a familiar example. You're in a car and you are driving in a big circle. So at this point, your velocity is straight north, and then supposing we look at another point, your velocity is kind of north-ish, west-ish. So the first characteristic of circular motion is that as an object is moving in a circle, the velocity is always tangent to the circular path. So at that far east point, my velocity is always going to be north. If I was at the northmost point of the circle, my velocity would be straight west, just like that. So, let's put you in my car with me as my passenger. As I go around this curve, you smash your head on my window. Why would I do such a thing? So, your head has smashed against my window. We're not sure why exactly your head has smashed against my window yet. It might be a force. We're not real sure yet. I know that with forces, I always have two objects involved. So one object is obviously your head, and the other object is, we're not sure of the other object. Well, let's look at another way. I started out going north, and then I started going less north and more west. So my acceleration and my force on my car seems like it's going inward, because if I'm going straight north and I want to go east, I need something to push me in that direction. West, I guess, in this case. If I wanted to go west, I would need something to bump me to go west. So maybe there's an inward force instead. We might be able to find our two objects on this one. We have, once again, your head, and, oh right, you smacked your head against the window. The second object's going to be the window. Okay. So this was an inward force. We have two objects here, so it seems like the inward force does exist. Let's talk about the green one some more. Since it doesn't have a second object, we can't call it a force. In fact, in circular motion, there's never going to be a force pushing to the outside. It may feel like it, but that's not a force. So what is causing your head to smack against the window? According to Newton's first law, an object in motion is going to stay in motion in the way that it was moving before. So we started off driving straight north. So your head, the car, everything was going straight north. When I started to turn, my car turned, but you want to continue straight north, and that's why your head smacked the window. So that's not a force. That's Newton's first law. Not a force. The motion of your head is due to Newton's first law, or the law of inertia. We did an example earlier with the one-dimensional forces where we talked about if you had dangly things hanging from your mirror. So here's a car again. Here's you in the passenger seat. If we were sitting at a stoplight and I accelerated suddenly, any dangly things I had from my mirror would swing backwards towards us, and if you were leaning forward, your head would lean back against the chair and the headrest. So even though you feel like you're going backwards, that feeling is because the chair, the headrest, is pushing you forward. It's the normal force being applied by the chair on your body. It's the same kind of thing, except in a circle. So, you might have heard this called the force of inertia, or the centrifugal force. No. Don't ever talk about these things in front of me, ever. They aren't forces. Like, it's not a force. It's due to Newton's first law. There's no force acting here. And to an observer, there would be no forces acting. So, instead of calling it a force, we could call it the centrifugal effect. That would be much better than calling it a force, because it's not. So, let's look... before we do that, centrifugal force. A lot of people get centrifugal and centripetal mixed up. The way I remember it, centrifugal has an F in it. It is a fake force. So both of those have an F in them. They're fake. They're not real. We have to call it an effect rather than a force. So, this inward force is called centripetal force. Centripetal means center seeking. So, it's going to point towards the center of the circle every time. So, now, let's take a look at my car from the back. So there's my taillights, there are my tires, there's your head smashed against the window. In this, we have, of course, our weight and our normal force. And we said that there's no force acting to the right. That's just due to Newton's first law, that your head is smashed against the window. The thing that's going to cause your force is the force of the window on your head. That's what you're feeling. And this is going to be the centripetal force. That brings us to two key facts about centripetal force and circular motion. The first is that both centripetal force and acceleration, since acceleration and force are so closely related, thanks to Newton's second law, they're always going to point towards the center of the circle, kind of like I drew over on the road. Always going to point towards the center. The second thing about centripetal force, it is an already existing force. It's probably a familiar force that we've worked with quite a bit. So there's no mysterious centripetal force that comes out of nowhere. There's something there causing it. So, for example, in this case, it's the force of the window on your head. Since the window is a surface, we can actually call it a normal force. It's the normal force from the window, perpendicular to the window, acting on your head. As another example, in elementary school, y'all might have played with tether balls. It was a horrible experience for me, but the thing that keeps the tether ball moving in a circle rather than straight out like a kickball or a soccer ball was the tension in that rope. Because it was connected to the pole with the rope, it would move in circles, and so that tension is responsible for keeping it in that circular motion. And then going back to the big picture, the whole reason your car can turn in circles is because of friction between its tires and the road. So centripetal force is always a force that we've worked with already. And the most important thing is that it doesn't pop up out of nowhere. Something has to be causing it. Okay? So we've talked about centripetal force. Let's talk now about acceleration. So let's say here's a circular path that I'm going to be driving on. Okay? So if I'm driving slowly, you aren't going to hit your head as hard on the window. Right? I mean, that makes sense. The faster you go around the curve, the more jarring of an experience it is. So if the velocity is slow, you're not going to smash your head as hard as when you're going fast. In other words, the centripetal acceleration is related to velocity. And it's actually related to the velocity squared. Essentially what I'm saying is that as your velocity goes up, your acceleration is going to go up. As your velocity goes down, your acceleration is going to go down, and that relationship happens to be related to the velocity squared. So it has a huge effect on the acceleration. Another thing that affects centripetal acceleration is how big your circle is. So before my circle was small, now I'm looking at a big circle. So if I increase my radius, if I turn really wide, like you're not supposed to do, that curve is gentler. You don't experience as much acceleration there. Whenever you make a really sharp turn, it's usually really jarring, and you usually clip a curb, or at least I do. So if I have a large radius, you won't hit the window as hard. So that's an inverse relationship. As my radius goes up, my centripetal acceleration goes down, and that's just a straight inverted relationship.